Oh, almost out of a big burp. I was checking Coca-Cola. I did say yesterday in yesterday's video I was gonna do a harder problem today. Oh, what's up, guys? Let me start off here. I'm getting ahead of myself. I already recorded this bit, but I got a call, so I'm re-recording. I just I'm not gonna edit it. Zero editing on this channel. I might edit later. But what's up, guys? Hey, Devs here. We're back with some more LeetCode. Doing LeetCode every day until I get a job. I hope y'all can't hear the washer going in the background. If you can, I'm so sorry for the audio. I'm kind of scrammed for time. Girlfriend gets home in 30 minutes. I need to record this video, cram for my test, and at least be done somewhat when she gets home. So today we're doing two problems, two easy problems. Even though I said also do a hard problem, I was busy today with the family. Taking the dog around. I was showing him to everyone. I was taking care of my sister. I was taking care of my nephew today, and just a busy day. So I decided to do these two easy problems. I thought they were fairly not, I mean, they were cool problems. Two easy problems. They're just basic recursion problems. So we'll go ahead and hop into this and I'll walk through the steps. So we're doing the sum of left leaves and then the count complete tree nodes. So this one just returns the count of nodes in the actual tree. So if you count them up, there's 1, 2, 3, 4, 5, 6 nodes. And then for this one, we want to take the left node of every node. So the root will never be a left node, right? Because there's no node above it. And the only reason it's the left node is if we call node.left, pass it the left node associated to it. So the only two left nodes, left leaf nodes, not just left nodes. The sum of all the left leaf nodes. I got my thing in it. The left leaf nodes right here. And a leaf is a node that points to nothing. It's the very bottom node. It has 0 children. So both of the pointers for 9 and 15 and 7 in this case, like all of these are leaf nodes because they have 0 nodes under them, right? So if you go ahead and draw out the rest of the tree, all of these point to null. Oh, what is that in? All of these point to null. So we know that these are leaf nodes if they point to null. The next thing we need to know is we need to know if it's a left node. So the only solution I came up with this is I overloaded this overloaded this function. So it's the same name. I just passed it a boolean and it is left. That way we can be able to distinguish left nodes from right nodes while we're calling it. And then later in the function call, we'll see if it is a leaf node. And if it is, we'll return that value. So for this problem, we're going to return sum of left leaves. And we're going to do our root. And then is left. Like I said, the root node is never a left node. And so we're going to pass false into here. And then we'll finally get into the meat of our function. And this is going to this is where we're actually going to get the sum of all the left leaf nodes. So the left leaves are 9 and 15, and them added together are 24, and that's the value they want returned, right? So the way I check this is if root is equal to null, we're just going to return 0. So that means we've made it past our function code. That means we've made it past a leaf, or we're at a null root. So we're going to return 0 because there's no value in it and it's not a leaf node. That kind of just saves us a little bit of trouble because we don't have to check if root is null later. And then from here we want to create I created an int sum, right? And this sum, we want it to hold the value of because a recursive problem, all it is you break a problem up. So we're going to call it for left and right, and we want to keep up with the sum that right gives us and left gives us, right? So we'll do int sum is equal to sum of left leaves, and we're going to pass the root dot left, and then we're going to pass it true because it's left node we're pointing to it. And then we're going to sum plus equal sum of, excuse me, left leaves, and then we're going to pass it the right node and false. So the next thing we want to do is we want to check if root dot right is equal to null, and if root dot left is equal to null. So this right here is checking to see if it's a leaf node, right? And it'd probably be slightly faster to check is left first. And this is what the boolean that we passed inside of it is for, because we want it to be a left node, because if it's not a left node, then there's no point in checking if it's a leaf node, right? Because then we're going to do nothing with the value. And we can go ahead and break out of this. So if it's left, and then if it's a leaf node, because that's all the root dot right and root dot left, both of those are equal to null. That lets us know it's a leaf node, and then this lets us know it's a left node. And if both of those are true, we want to return the root dot value plus some. No. Okay, and then we can just do root dot value. And then if we don't go inside this if statement, then we know it's not a left node and it's not a root node. So we just want to return the sum. And then that should be right if I'm not missing any semicolons. Should run for all the test cases. And then if we submit it, it should run in 0 milliseconds. There we go. Time complexity is O of n, where n runs this block of code for every node. And then the space complexity is also O of n, where it calls a function for each node, because each node gets called this function recursively. And so the space would also be, it might be n divided by 2, but you know, we just count the n. It beats 100%. So we'll walk through this one time. So it gives us this function call, but I don't like the function call because I don't know if the node we're looking at is a left node or a right node, right? So I made my own passing a boolean so we can see if we pass it, in this case the left node, and then in this case the right node. So then from here we can see if it's a left, and then if it's a leaf node, we want to return the root dot value, because if it's a leaf node, then the sum is going to be 0, because you see root equals null equals 0, it returns 0. So the sum of left leaves and sum of left leaves function call on the left node and the right node will always return 0, because if it's a leaf node, then the nodes it's pointing at is null. So those will return 0 for no matter what. So we can just return the root dot val. And then if it's not a left node and it's not a leaf node, then it could be like the 20 node right here. This will return the sum of 15. And this will return a sum of 0. So it won't return this value. We need to have it return something at the very end. So, and then the sum of this would be 15, because 15 will be passing the sum first, and then sum plus equals the right node sum, which is 0. So sum is 15 in the function for 20, the 20 node. But we don't want to add the 20's value, so we just want to return the sum, and then it'll pass 15 up to 3. And then same thing goes for 9's. It's going to see that 9 is a left node and it's a leaf node, so it's going to pass 9 up to 3. So then 9 plus 15 equals 24. 3 is not a left node, 3 is not a a leaf node, and it's also not null, so it's going to return 9 plus 24, which is what's held in sum, and it's just going to return something at the very end. And that's pretty much it for this. I thought this recursive problem was fairly simple. You just keep up with the sum, and you only want to return the value if you know it's a left node and it's a leaf node. Other than that, you want to return the sum of all the function calls below it. So the next one is actually even easier. I think it's only like 3 or 4 lines of code. and I didn't believe how easy it was, but count complete tree nodes. So a tree node is a tree node if it's not null, right? So if root equals null, we'll return 0. Because if it's null, then it's not a node, right? So we just want to return 0. We don't want to count that node, so we return 0 for it. And then from here, we'll return count nodes root dot left plus count nodes root dot right. So this gives us the count of all the nodes to the left and all the nodes to the right. So, and then we also want to count the current node we're at, so we'll give it a +1 at the end. So at the very ends, you can imagine this function call, like 1 will pass into here first. It will see that 1 is not null, so that it won't return 0. And then it will call this return function. And then this return calls two more methods inside of it. It calls it for a left node and the right node. So count node gets called to 2 and 3. It sees that they're not null, so it returns its left node and right node's count all the way down to the base. So we'll go ahead and start from here. We can go ahead and scroll down so y'all can see it. So as you know, if it's a leaf node, it points to two nulls. Nulls return 0, so you can imagine 0 and 0 get returned up to this return statement. So for 4, this is a 0, this is a 0, and then it's +1. So 4 is 1. And then the same happens for 5 and 6 because both of its nodes below it are null. So they'll return 0s for the count node function call, and then it will get added 1 for the current node we're at. So then 2 originally called count nodes for 4 and then count nodes for 5. No, these two nodes. So for 2, let me not do that. We'll use the eraser. For the 2 node right here, it gets passed a 1, as we see here. And then it gets passed a 1 over here. And then it gets added 1. So 2, the count is 3, which is correct. I mean, if you count the nodes from 2 and under, it's 1, 2, 3. And so we want to return 3 to the 1 node. Then 1, that's for the count nodes root dot left. Then we'll do the count nodes root dot right. 3 also isn't null, so then it will call these two functions for itself too. This 3 points to a null node right here. So this will return 0, and this will return 1. So in the case of the 3 function call, I just erased all my work, but 1's here, and then this null node right here returns 0. So for 3, the function calls will return 1, 0, and then we're counting the 1 for the current node we're at. So then 3 will have 2. And this 2 node will have a count of 3 nodes, and this has a count of 2 nodes. And if you count them up, you see 1, 2, 3, and then 1, 2. And then these get passed to the original function call, 3 and 2. And then if you go ahead and erase these. So for the original function call, these two methods or functions gets returned the 3 value, and this gets returned the 2 value. And then it adds the node that we're looking at. So 1 will get added 1 to it. And then so 3 plus 2 plus 1 gives us 6. And if we go ahead and count the nodes, we have 1, 2, 3, 4, 5, 6, which is correct. We have 6 nodes. We return that value at the very end, and that should work. So if you run this, apparently I can't code. Oh, that would make sense. So if you spell your function calls correctly, then your code should run. There we go. Runs in 0 milliseconds. We'll go ahead and see the solution submitted. Runs in 0 milliseconds, but it's 100%. And once again, we have 2 more LeetCode problems solved. I solved this problem, let's see, 28 minutes ago. that first half of the video was a bunch of jabbering, which is the same with this video. But we got two problems done in about 14 minutes. So yeah, I mean, this one's a fairly simple. Like I said, it was 3 lines of code. I figured it was 3 or 4. And then this one was a bit more complicated, just because we have this if statement. We're only returning a value if it is the actual left leaf node. And other than that, we're going to see the sum of the left and right nodes. So once again, we're recursively calling, and then we check the root node if it's null. And then if we submit both these examples, we can see they both be 100% with 0 milliseconds runtime. The space and time complexity of both of them are O of n, where n is the size or how many nodes are in the tree, and the space is n because it calls that many functions for that many nodes. And then this time complexity is also n because there's no recursive loops, but there is it does run this block of code for every node, and same goes for this. It runs this block of code for every node. So do a little time complexity and space complexity calculations. It's always great. It's always good to analyze your algorithms to make sure you know the complexities. I've gone over that a few times, but I feel like I'm just rambling here at the end. But that's going to be all for today's video. If you have any questions, comments, concerns, please leave them down below in the comments. And be sure to like, be sure to subscribe. I'm going to keep on doing this until I get a job. So maybe we'll hit day 300, but hopefully I get a job before then. Day 300 will be in the middle of my last semester in college. Maybe I'll have a job lined up before then, or at least looking. I hope I'm not working at Panda Express still by that day, but who knows? Only future will tell. Maybe ChatGPT will run everything that has to do with tech, and I will just have to sit here and watch it and goon in the corner, I guess. The goon question employer if you watch this video. I did not say that. It was just a joke. Anyways, I'm not editing that out. I'm not editing that out. But I hope you have a great day. Y'all stay blessed, stay healthy, stay coding, and I'll catch you on the next video. Hey Debs is out.